Welcome to the Sun Today for the 30th of March 2022. And today we're going to look at why the Earth's magnetic field is getting so upset. But first let's take a look at what's been going on in the Sun over the last few days. You can see in frame 1 at the top left there that the sunspot number is stubbornly round about 80 and has been for the last week or more. That's quite a high level of sustained activity for this time in the cycle. The planetary KP index has been quite unsettled for the last few days, including a short period where it was in a geomagnetic storm, albeit a minor one. And that's what we're going to be expanding on later in the video. In frame 3 we can see the GOES X-ray flux. There was the M2 flare yesterday and we've had a C5 flare this morning. The general background is up to about B6. In the fourth frame you can see the sunspots with respect to the background corona. We've lost a couple of regions over the limb and two of the regions are decaying. However, region 2965 still is dominant with a large number of large sunspots, and we've had three new regions appearing. Now I don't know whether they're going to amount to much, but the one in the northwest actually was the source of the C5 flare, which was a bit of a surprise. We've had 3 months since the last spotless day on the Sun, and one wonders how long this is going to go on. It certainly looks as though we're going to make 100 days. We've had 12 consecutive days with at least a C1 flare during that period. This is a cartoon of what the Earth's magnetosphere looks like, and most of us, I'm sure, are familiar with pictures like this. You can see the Earth in the center there with the Earth's magnetic field shown in red. Now there's a boundary between the Earth's magnetic field and the interplanetary magnetic field from the Sun, and that's shown in this sort of blue color. That's the magneto sheath. The edge of that's called the magnetopause. As a solar wind comes in, it's slowed by the magnetosphere and creates a shock. It's called the bow shock. You can see it with those squiggly lines there. However, what we don't often understand from seeing a picture like this is that this is a very dynamic situation. Solar wind comes in and it's variable all the time. So this boundary moves backwards and forwards. And so one can only conclude that the magnetosphere is going to be dynamic. And so what we will do is we'll now take a look at a video, or a model at least, of what the magnetosphere changes like during one day. Here we take a look at what is actually prompting the magnetosphere to change so much, and that's the characteristics of the solar wind. You can see here there are three major quantities you want to take a look at. That's BZ, that's the vertical component of the interplanetary magnetic field, and that's what reconnects with the Earth. The density of the solar wind, that gives you the amount of mass that's coming towards the Earth, and then also the speed of the solar wind, which could vary from anything from less than 300 to over 600 kilometers per second. And you can see in the last 3 days, this is a 3-day plot, that BZ has been fluctuating both above and below the zero level. When BZ turns negative, i.e. that means it's pointing southwards, that means it can reconnect with the Earth's magnetic field. That's what opens the Earth's magnetic field to geomagnetic events, such as geomagnetic storms. You can see the density has been fluctuating wildly from less than 1 particle per cubic centimeter to one stage here about 50 particles per cubic centimeter. And the speed of the solar wind has also been fluctuating. We were down to nearly 300 at one point, and that speed almost doubled the last 12 hours. What causes the problem between the solar wind and the Earth's magnetic field is when something called magnetic reconnection occurs. That's when opposing fields reconnect, releasing a lot of energy. And you can see it here with the Earth's magnetic field here is shown in green. That's the stable field. But as the solar wind comes in, if it's oppositely directed, it will reconnect with it, stripping away some of the outer layers of the Earth's magnetic field and depositing a lot of energy into the system, that energy transmits to the tail of the Earth's magnetosphere, which is many millions of miles downstream away from the sun. When those two oppositely directed magnetic fields connect, they then release particles that stream back towards the poles and create the aurora and the geomagnetic storms. And we have a lovely illustration from NASA here that I'm about to show. So what can we conclude from all of this? The solar wind is becoming more active as solar activity levels rise. That's from more flares and more coronal mass ejections. The more solar wind fluctuates, the more geomagnetic storms we're going to have. So we could look forward to, as solar activity rises, more geomagnetic storms. Thank you for watching. If you enjoyed this, please pass it on to others who might enjoy it as well. So until next time, stay safe and goodbye.